All right. Can everybody see my screen?
Yes.
All right, cool. All right. So the last question that we did was this one where we went through and resolved all of the chemical shifts for this compound that with this ketone down here. So we're going to move on to the next spectrum. So let's look at it. Same. And again, for the IHD, you can calculate that on your own because we covered that in part one. It's same as calculating the degrees of unsaturation. So this compound, it says it's C4H10O is the molecular formula. And how many signals are we seeing here? Not lines now, signals. How many signals are showing up on that spectrum?
4.
4 signals, right? We got a signal here, 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 and here. Now let's go back up to our compounds because we already went through and said was what and how many signals we should see. So we know it can't be this compound right here, right? It can't be that one because that's 3 signals. We already resolved that. And it can't be this one because that's up to 7 signals. And we already finished the spectrum for that one. So it has to be this compound right here, right? Let me erase this stuff so I can grab the actual compound itself because we already talked about that. Oh, wait a minute. Wait. I'm gonna leave it because I haven't posted. I didn't post this, I don't think. Or did I? That's okay. I'll just draw it. Okay, let me just draw it in. And then we're gonna go through and pick out. Right? And so remember I said, let's go ahead and get the OH proton out of the way. Because remember I said sometimes you'll see it and sometimes you won't see it. But if you do see it, it won't split. And so right here, you can see that that's an integration of 1. So this proton right here is going to be the OH proton. So depending on what type of instrument you're using, sometimes you'll see the OH proton, sometimes you won't. It just depends. All right. So now we got 3 signals left to resolve, right? We got these protons right here. I'm going to just color code them so we can color code them on the spectrum. All right, so we got these protons. We have these CH3s up here. And then we have this 1 proton right here. All right. So which ones would you expect to be the furthest downfield? Remember, downfield is away from 0, electron poor environment. Upfield is towards 0, electron rich environment.
The hydrogen's next to the OH.
Yes. These protons right here, right? We call these, if it's on a carbon that's adjacent to a hydroxyl group, we call them carbonyl protons. Carbonyl protons. So that you're exactly right. And then if you look at, so we're saying that this signal, wrong pen, sorry. We're saying that this signal is representative of those protons, the pink protons. And that's exactly right. Why is it split into a doublet?
You're asking why is what split into a doublet?
The signal right there at 3.4.
Because it has an adjacent proton.
Yeah, look at the molecule. The pink highlighted signal is for those pink protons. All we have to do is look at what's next door. Remember, the OH is not going to couple. Right, so this proton right here, no coupling.
So that just
next to.
Then that just leaves a CH3.
It's not it. You mean the CH3 or the CH next door to it? You see that? It's got to be adjacent. So it's got to be on this carbon. These two carbons are going to talk to each other. This carbon here is not going to talk to a carbon way over here. That's too far away. So the only time you see splitting is when they're right next door to each other. So that's why it's a doublet, because it only has one neighbor, right? So for that proton, N is 1. And N plus 1 is 2. So it's a doublet. And the reason it's so far downfield is because it's adjacent to the OH group. All right. What about the signal here? What do you think? Which proton is that?
The blue one.
The blue one. So let me highlight that in blue. So right here, this signal is this proton right here. That's exactly right. And if we look at that proton, how many lines is that split into? Let me zoom in so you can see it. Let's count the number of lines. All right, so 1, 5, 6, 7, 8. It's 9 lines. Can y'all see that? You see the two little shoulders on the outside right here?
Yep, see them.
So that would be that proton is actually split into 9 lines. So for that proton, N is 8. N plus 1 would be 9. And we can look over here and see immediately you got 6 protons adjacent to it with the 2 CH3 groups. Here and here, that's 6. And then you got 2 protons on this carbon that's also adjacent. So that's 8 protons total. N equals 8, N plus 1 will be 9. So we're just going to call this a multiplet and not a nonette. That just sounds dumb to me. We'll call that a multiplet. All right. Any questions? All right. Now, and then you see down here at 1, again, all of these chemical shifts are on purpose, right? Things show up where they show up because of their chemical environment. So those methyl groups are showing up in the range where alkyl groups will show up, right? If there are no really, not a lot of functional groups present. So somewhere between 0.1 to 1, anywhere in there, right? When you put more electronegative functional groups on, then they start shifting a little bit further down. But when the last signal is this one. And that's for these protons right here. Why don't I see 2 signals for those?
Because they're equivalent.
They're equivalent, right? They are equivalent. All I have to do to test for that is take one off the top carbon, take a proton off the top carbon and stick another atom on there. And then I'll take one off the bottom carbon and stick another atom on there and compare the structures. They're the same thing. Why is it a doublet? We can see that it's a doublet, right?
Don't they have? Yeah.
Say that again.
It's adjacent to 1 hydrogen.
One proton, right? This set of protons right here. Let me erase this. Right here only has 1 neighbor right there. And because they're equivalent, they're going to see the same thing. So that's going to show up in the integration and not in the number of signals. And you can see the integration is 6 because it's that signal is representative of both of those CH3s. So for this N, N is 1. So N plus 1 is 2. It's going to be a doublet. And the reason it's showing up at 0.9 is because it's just those are just regular alkyl protons, right? And this isopropyl proton right here showing up at about 1.8, right? That's easy to pick out, and it's pretty typical for isopropyl type proton. It's the same. You're gonna see that anytime you see this type of motif right here, where you have a proton kind of hemmed in by two methyl groups, that's the splitting pattern that you're gonna see, or something similar to it. All right, and then let's look at the infrared right quick. What stretch in the infrared is going to confirm to us that this is the right compound for this spectrum?
I look at the hydroxide one. I just know that's the first one.
Right here, the hydroxyl stretch right here.
Yes.
Yes, that's exactly right. This is an OH stretch. It's always going to show up in the same or a similar at a similar wave number, 3,300, 3,400, but that it's the broadness of it that gives it away. It's a fat, broad stretch. And so that OH stretch, if you see that, you know that you have an alcohol group present. And then right here, this stretching right here, that's your alkyl stretching. Anytime you have carbon-carbon single bonds, where everything is all saturated, you know, like the methyl groups and the CH2, everything is saturated. There are no double bonds and all that stuff. It's just carbon chains. That's what the stretch looks like. It's an alkyl stretch. And it's the same range, somewhere between 2,800 and 3,000. But you can tell it because of how jagged it looks. It always looks jagged like that. And then the only other stretch in here that's important is right here. This stretch right here. That's a carbon-oxygen single bond stretch. Right, in the infrared, that when you see that stretch, it confirms that you have a CO sigma bond somewhere in your molecule. What the thing about infrared is, you don't know where the functional groups are. That's why you need to combine it with another method like NMR, right? Infrared only tells you what's there, but it doesn't tell you where it is. It doesn't tell you anything about the structure. It just tells you what functional groups are present. But the NMR can tell you a lot about the structure, because the way those signals split tell you how the carbons are connected to one another. And this can get much more complex, by the way, like a lot more complex. But we're going to look at some complex examples. If we have time today, we'll look at some today. Look at least one. And I'll talk about like the complex splitting. All right, so let's go back up to here. We only got one, so we already did. No, actually we did. We got two left to do. So let's look at the next spectrum and see what we got. We only got one compound up there that is 3 signals, and it was this one. All right. So that compound said that when we went through and resolved it, we said it would give us 3 signals. So the signals are going to be here for the hydrogens on this CH3, here, and then of course we got 2 hydrogens here. Right, and those are going to be a signal. Anybody not see that or have a question or not, just not catching it? Because if you're not, say something. All right. So you see the molecular formula over here, C4H8O2. You can calculate the degrees of unsaturation is going to equal 1 because you only got 1 pi bond present. And then, so let's go through and pick them out. I want to turn y'all loose on this one. So which signal do you think is going to be representative of the yellow set of protons? The yellow CH3.
The first.
The first one at 1 or at 3.7?
The one closer downfield.
Yeah.
Here, right here.
Yes.
Yeah, I agree with that. And then you can also see right here, the integration is 3. So that's telling you that that's representative of those 3 protons. And it's a singlet. Why is it a singlet?
Because it has
yeah.
It's got no neighbors, right? There are no hydrogens next door to it that can split with it. It looks like this, right? It's O. Let me move that over. So it's O like this, and then C with 3 hydrogens on it. And so there's nothing next door that it can split with. And so that's why it's a singlet. And of course, those 3 hydrogens are equivalent to each other, so they're not going to split each other. All right. What about the green set? Where is that?
the second, number 2.
All right, good. Right here, right? For that, N would be what? 3, and then
3.
1,
4.
4, which would be a quartet. It looks like quintet, my bad. So that's a quartet. And you see that, right? And you can see the integration. Integration is for 2 protons. All right, and then down here, obviously we only got 1 signal left and 1 set of protons left. So that's going to be the pink set right there. And you can see the integration is 3 protons. And then why is it a triplet?
Because N is 2, and then N plus 1 gives you 3.
Good, 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 very good. So N equals 2 in this case. And N plus 1 is 3. Great. All right. And if we look in the infrared, the important stretch in the infrared is right here. Right. That stretch right there that you see, that medium stretch at 1743, that's your carbonyl stretch. And that's going to be anywhere from 1700 to 1800 reciprocal centimeters.
Dr.
Yes.
How are you identifying the stretches, like for a carbonyl?
If you're looking at in the video that I sent, there's a chart in there that goes through each type of, actually there's a slide for each functional group. Well, not each functional group, but for the major functional groups, there's a slide that talks about the ranges where they show up.
Are we going to go deeper into that today or like next class?
No, because I'm really trying to just keep the focus on NMR and just slide the infrared in there. But that infrared, the introductory video, it gave like all the stretches. What does it mean about reciprocal centimeters? What are the different types of molecular motion? Because that's what infrared does, is it's basically you bombard a sample with radiation in the infrared range. And then different functional groups pick up or they absorb radiation at certain wavelengths. And that's what makes them move or vibrate or twist or wag or whatever the motion is that it picks up. And then when they absorb that radiation, that's where they show up. That's where the stretches show up. And the intensity of the absorption is reflected in how intense the stretch is, right? So, I mean, I mean, we could do it, but it'll probably be Friday if that's something that is just not clicking. But as far as the stretches are concerned, there's just a table with the different stretches on it.
Okay.
All right, we got one more structure. And then we're gonna do an example with what we call complex splitting. I'll send that complex splitting video later today. And then we'll do more of that on Wednesday. And then on Friday, we'll just have like a work day or something like that. Let's see. Let me go up here and grab this. So the last one, the last structure is the one with the aromatic ring in it. So let's go down to that spectrum because we've already solved all the other ones. Let's go down to that spectrum and walk it down. I think the nitrogen was there. Uh-oh. Yeah. So that's my, this is the structure that we're looking at. And let's do the chain first because the aromatic protons are all going to show up in the same region. You can see right here, the aromatic protons are going to show up somewhere between 7 and 8.5. And that's standard. That's the standard chemical shift for aromatic protons, somewhere between 7 and 8.5. Let me fix that up. All right, so you got protons here on the chain, here, and then the CH3 out there. And you can see right here for the aromatics, you can see that this is integrating, this whole section is integrating for 4 protons, right? So you got a proton on each one of these carbons that's left over. All right, so let's look at the chain first. All right, so we got no equivalent protons on that chain. So that chain is going to give us 4 signals. All right, we just need to, this is where knowing the N+1 rule really helps. And also knowing like where certain protons are supposed to show up helps a lot, right? Because if you look at the chain, none of this stuff is equivalent. Everything is different. So you got a set of protons here. You got a set here. You got a set here. And then you have a set here. So all 4 of those are going to show up down there in that section. And you can see it. Right, you can see the protons down here and you can see how they're split and everything. So let's start at the end of the chain. Which one so first of all, let's approach it this way. What should this signal for these protons be split into? Should it be a doublet, a triplet, a quartet, a singlet? What?
A triplet.
Should be a triplet. Right? So when you look at the spectrum, how many triplets are on the spectrum?
2.
You got a triplet down here at 2.6. You got a triplet at I'll say 0.95 or 1, right at 1. So now the question is, of those 2 triplets, which one do you think is representative of the CH3? There's a couple of ways to think about it. First of all, you need to think about the chemical shift, like which one is downfield, which one is upfield. The other part is you can look at the integration, right? If you look at the integration for this triplet and this triplet, you can see that there's a difference.
Wouldn't it be more upfield?
It would be more upfield. That's exactly right, because it's further down that chain away from that aromatic ring. Right. So, and the integration also tells us that is that triplet is for that orange set of protons, because that signal is integrating for 3 protons. And then the triplet down at 2.5 or 2.6 is integrating for 2 protons, right? So that's how we can pick that out. So we'll say for that, N is 2, N plus 1. It's 3, so it should be a triplet. and the integration should be 3. All right, now let's do the other triplet. Why is that triplet further downfield, and which set of protons does it match?
Is it the blue hydrogens?
The one all the way closest to the ring. That's exactly right. And there's a couple of ways to think about that. Let me go back down here and make that orange. There's a couple of ways that you can arrive at that conclusion, right? Number one, we look at the splitting pattern of it being a triplet. So it has to only have 2 neighbors, right? So N in that case is going to be 2. So N plus 1 will be 3. So it should be a triplet, right? And if we look at the chain, which one of those sets of protons matches that? Right, the one on the end has 2 neighbors, the orange set. The one next to that doesn't, because it's got 2 on one side and 3 on the other side. The purple one has 2 on each side, but the blue one only has 2 on the right side of it and nothing to the left of it. Are y'all following that?
No. You said, could you ask what other which other set is like the blue set, right? Is that what you asked?
No, I was asking why the blue set was a triplet, because that's what we're looking at, right? We're looking at now. We're saying that it's a triplet, but if we look at the chain, we need to. If I didn't have it color coded or marked, you should be able to look at that chain and say, "Oh, this should be a triplet because it only has 2 protons on, neighboring it." And the only other set in there like that is the blue set. Right, so that's how we can look at it that way. We can look at the integration, but then the other 2 signals also integrating for 2 protons, right? This signal right here and this signal right here, they both integrate for 2. But then the other way to look at it is by looking at the chemical shift, right? It's next to an sp2 carbon, because that carbon in the ring, I'm gonna try to pick a different, there we go, we'll use that. That carbon is sp2, right? So protons that are adjacent to sp2 carbons show up between 2 and 3, right? And you can see that signal showing up at about 2.6, right? So there are a lot of ways to like decipher or figure out which signal goes where, right? We have a lot of clues here. We have the integration, we have the splitting pattern, and we have the location. Those 3 things are like good ways to tell if you only had the structure and nothing else, right? You can look at the splitting pattern, you can look at the integration, and then you can also look at the location to figure out which set of protons that signal will represent. All right, what about the 2 in the middle?
One is a pentet and the other one is a sextet.
Good. So if you look at the 2 signals here, I'm zooming in, right? You see here 1, 2, 3, 4, 5, 6 lines. So that's a sextet. And then over here, 1, 2, 3, 4, 5 lines. So that would be a pentet. Right. So that's how you would tell those apart. And if you look at the structure, which one of those, it's going to be either the purple or the green, right? Let's look at the purple one. What would that signal, what would the coupling or the multiplicity be for that signal? The splitting pattern.
So N would be 4, right?
Yes, it's got 4 protons adjacent to it. 2 on the left, 2 on the right. That's exactly right.
So N equals 4, and then you're gonna get 6.
Right, so N plus 1 would be 5. So that's your pentet. The purple protons would be your pentet. So this one right here is going to represent that purple set of protons. All right, questions about that? And then for the sextet, obviously, it's the last set of protons, but we also need to know how we got there. So how does that signal get split into a sextet without just doing process of elimination and saying, oh, that's the signal for that?
It's surrounded by 5 hydrogens, so yeah, it has 5 neighbors.
Yeah.
So then you'll add 1 and you'll get 6, so that'll make a sextet.
Right. So we're gonna find the right color pen. So for this one, N is 5, N plus 1 is 6, right? And as long as you are able to, if you're able to apply the N plus 1 rule, either backwards or forwards, you'll be good, because you can resolve these signals fairly quickly if you understand, like, oh, it's a sextet, so that means that it has 5 neighbors. So let me find a proton in this molecule with 5 hydrogens around it, right? That's how you should be able to apply it both forward. That means looking at the protons and saying, oh, this should be a sextet, or backwards. That means looking at the sextet in the spectrum and saying, oh, this should have 5 protons around it, right? Because when you take the exam, that's what you're going to see. You're going to see both problems that might give you a signal and ask you to pick out the protons, or it might give you the protons and ask you to pick out the signal. All right, and you can see in the aromatics, how many signals would you expect for the aromatics?
3.
I would say 4. Expected.
4.
Oh, expect. Sorry.
Yeah, no, it's okay. You got 4 protons, right? So I would expect that to be 4 signals, but 2 of those protons must be equivalent because you only have 3 signals. Are you following me?
Yes.
Yeah, so 2 of them have to be equivalent. My hunch is that it would be either these 2 that are equivalent, I think it'll be those 2. Just for the fact that if you replace one of those 2 with a different atom, and then you rotate around the sigma bond here, rotate around that sigma bond, I think those 2 will be equivalent. All right, any questions about that?
Yes. How are those 2 equivalent again?
So with those 2, you can rotate around this sigma bond right here that I have highlighted in green. You can rotate around that bond. So if you put another atom where that top proton is or where the bottom one is, and you rotate, you're going to get a similar structure. But the point is that you see those 3 signals. So that means that you got to have some equivalence on that ring somewhere, because otherwise you will see 4 signals down there, unless 2 of the signals are overlapping, which is quite possible. All right, any other questions about anything? Okay, so I want to do one example from here. This is the next handout that we're going to start. And I think when I uploaded this to I can't do it now because I'm on my iPad, but I think when I uploaded this on Friday, I think it was Friday, both of these were in there. I think I put both of them in there. But I want to do this example right here, because I want to talk about one other topic. And that is, like, sometimes when you have stereo centers present, and we do have a stereo center right here where the OH is, it causes what we call multiple non-equivalence. Right, and when you have multiple non-equivalents, you don't get like just your standard splitting patterns. You actually get what's called complex splitting patterns. And so what happens with those complex splitting patterns is sometimes, like you might say, oh, that should be a triplet. But because you have some functional group causing this multiple non-equivalence, you don't necessarily see a triplet. And I'm gonna show you with this example what that is. Right, so let me find the spectrum for it. All right, so with that example, you can see in the infrared, you got a couple of stretches here. You got your OH stretch showing up, but then you have an NH2 group, which is gonna have a similar stretch to an alcohol. So you got that showing up down here as well. Let me change the color on that. All right, so this is NH, and then that's OH. All right, so those stretches are going to show up in the infrared in similar places. And then down here, let's go ahead and get rid of those protons. Down here, you got the OH proton. I'm going to make that green. All right, so you have the OH proton down here, and then the NH right here. So that's out. So they're showing up, but again, they won't split. They won't couple. So that's two of my signals right there. And then what you'll notice that you have left a CH3 right here. And then you have a hydrogen here on a dash. And then because the stereo center that's next door to this CH2, those hydrogens are going to be non-equivalent. Normally, if that wasn't a chiral center, it wouldn't matter. But the fact that that chiral center is there, that makes these two non-equivalent. So the chiral center is going to make those two non-equivalent, and they're going to be called diastereotopic. The reason they're diastereotopic is because if I swap either one of them out with another atom, I would get two diastereomers as a result. Let me just go ahead and show you that. So if I did this, awesome. Let's say I put a bromine there, like that. And I did this. Like that, right? Those two compounds, when I compare them, they're diastereomers, right? They're not enantiomers. So that's why two protons adjacent to the chiral center are going to be called diastereotopic. Write that in here too. Right? So they're adjacent to the chiral center. And because they're non-equivalent, we got to treat them separately. So they're going to give you separate signals. All right? So they're non-equivalent due to the chiral center. And because of that, there'll be separate signals. Right? So when we look at that compound, how many signals do we have left, or should we have left? We already counted the oxygen or the hydroxyl group and the amine. How many signals should we have left in that spectrum that should show up? Knowing what we know, that those two hydrogens next door to the chiral center are going to be separate and non-equivalent.
4.
4 signals, good. So we should have a signal. I'm gonna go ahead and mark them. A signal for here, and then here. I mean, not doing them all the same color. Here, and then the CH3. Right here, right? So we can do the CH3 first, right? That's not going to be anything special because although a chiral center is next door to it, that particular carbon is prochiral, right? You can't put anything on it to make it chiral because you're going to have two groups. If you change one of the hydrogens out, you still got two of the same groups, two protons. So what should that signal be? How many neighbors does it have?
Is it 1?
Yeah, it's next door to that carbon with the hydroxyl group on. So for that, N is going to be 1. And then N plus 1 is going to be 2, so it should be a doublet. And we can see it's down in where alkyl protons show up, somewhere between 0 and 1, right? Now, the proton that's on the carbonyl proton, where the oxygen is, right? What do you think? That's going to actually be, in this particular case, it's going to be resolved like normal, like a normal N plus 1. We can just apply the N plus 1 rule to it. So what do you think? How many neighbors does it have? Even though those two protons adjacent on that adjacent carbon are non-equivalent, we're going to simply apply the N plus 1 rule. So we're going to count them together when we're trying to do the coupling or the splitting pattern for this proton right here, right? So it's got 3 neighbors on the left. Is that right?
Yes.
And 2 on the right. Is that right?
Right.
Okay, so that means it should be a sextet. That means 5. And then N plus 1 equals 6. Right, so then we're going to, that sextet is here. And you can see it if I zoom in on it, you can see it's 1, 2, 3, 4, 5, 6 lines, right? So the only other protons that are left are these, right? And you can see the signal for that is really already weird. I don't know why the resolution is bad on that. But you can see it as each one of those signals is 4 lines, right? I know if you look at the bottom, just at the bottom, it's kind of, I don't know how it got screwed up like that. But on the bottom, you can see there's 4 lines in that signal, and each one of those signals, 1, 2, 3, 4, like that, and then here. So each one of them is 4 lines. I'm gonna try to fix that and make sure that the resolution is right before I post it. But let's just take the pink one, just the pink one, right? We know why they're downfield like they are, right? The pink set and the purple set, that one of those is going to be the pink one signal is going to be for purple. But the reason why it's 4 lines is because of that non-equivalence. Normally, they would be a doublet. Is that right? Because it's not going to split with the NH2 at all. So it would only split with the 1 proton next door, which is the orange one. So it would just be a doublet. But the fact that they're non-equivalent, that pink proton is going to have coupling here between these two. And it's going to couple with the one on the same carbon with it because they're not equivalent. So it's going to couple here as well as here, right? So we have to consider the splitting pattern for that. It's going to couple twice. It's going to couple to the orange. It's going to couple to the purple. So it's going to be, for the orange one, N will be 1. Let me use the right pen. N is 1. Everybody agree with that? So for the orange one, N is going to be 1. And then for the purple one, N is also going to be 1. So what happens is that signal gets split into 2 doublets. right? And so that's why you see 4 lines up there, because the signal is split into 2 doublets, and we call it a doublet of doublets. I know that's weird. We call it a doublet of doublets because it's 2 doublets, but both doublets are representative of the same proton. You can see the integration is still just 1 proton, right? So those 2 doublets for that one, and then the purple one, you're going to get the same thing. It's going to couple with the pink, and it's going to couple with the orange. So you're going to get a doublet of doublets for that one too. I'm going to stop right there, and then we're going to pick this up on Wednesday. And we're going to keep talking about this complex splitting. But I'm going to send you a video today discussing it, dealing with it, and then we'll pick it back up on Wednesday.